Clouds are the most visible manifestations of weather. They blanket the ground as fog, glower with the threat of an approaching storm, or drift across a bright blue sky in ever-changing patterns of white and gray. In early morning and at sunset, clouds catch the rays of a low-angle sun and turn to glorious shades of gold, orange, and red. Clouds are visible because they are made up of tiny water droplets, ice particles, or a combination of water droplets and ice. They serve as the source for all forms of precipitation and affect the Earth's energy budget by absorbing and reflecting incoming solar radiation. Until recent times, anticipation of changing weather was based primarily on what observers could see of the sky. Thus, a knowledge of cloud types and patterns, reading the clouds, has long been important in interpreting and predicting the weather. Today, meteorologists can measure atmospheric conditions in a variety of ways, but their weather predictions still rely heavily on interpretation of cloud patterns as viewed from above by satellite sensors. Nearly all clouds and weather systems occur in the lowest layer of the Earth's atmosphere, a zone known as the troposphere. As can be seen when a thunderhead reaches its maximum height and begins to spread out into an anvil shape, the tops of most high clouds extend only to the tropopause, which is the transition zone between the troposphere and the stratosphere. As an air mass rises through the troposphere, it expands and cools. This is called adiabatic cooling. At the tropopause, the cooling ceases. The thin air of the stratosphere beyond is generally too cold, dry, and particle-free for much cloud formation to occur. Water vapor, necessary for cloud formation, collects in the atmosphere as water evaporates from oceans, lakes, and rivers, or transpires from vegetation. This invisible water vapor is picked up by moving air masses. When an air mass reaches its maximum capacity to hold water vapor, the air is said to be saturated. Because warm air can hold more water vapor than cold air, an air mass can also become saturated by cooling to the point at which the water vapor in that air mass reaches the maximum amount the air can hold. The amount of water vapor in a mass of air is expressed as the percentage of the maximum possible amount for air at a given temperature. This is the relative humidity. When the relative humidity reaches 100%, atmospheric moisture begins to condense into visible forms. These include clouds and fog, which is a cloud that touches the Earth's surface. Frost and dew also result from condensation of water vapor. The temperature at which condensation occurs is known as the dew point. The water droplets, or ice particles, that make up clouds develop as the water vapor in air cools past the dew point and condenses onto airborne dust or salt particles called condensation nuclei. Air cools past the dew point when it comes into contact with a cold surface, as when a warm air mass moves over a cold ocean current, or when air near the ground cools beyond the condensation point, producing a layer of fog. A majority of clouds, however, result from the cooling that occurs as air rises in the atmosphere. Orographic clouds form as moist air is uplifted over mountains. Commonly, a peak clear in the early morning is obscured by clouds a few hours later. Air may be cooled below the dew point along a frontal system when a cold air mass moves beneath a warm, moist air mass. Convection currents, or thermals, generated over warm surfaces, such as the heating earth on a summer day, also cause air to rise. Before they reach the dew point, these air masses are not visible, but one can watch glider pilots who seek out the thermals for the lift they provide in the lower layers of the atmosphere. There is little or no exchange of heat energy between such a rising parcel and its surroundings, so the air mass expands and cools. Cumulus clouds resulting from convection begin to form at the condensation level, or the level at which the rising air cools enough to reach its dew point. As seen from the ground, the flattish bottoms of these clouds indicate the position of the condensation level. Heat energy required to condense water vapor into water droplets slows the rate of rise, but under proper atmospheric conditions, adiabatic cooling continues as the cloud mushrooms upward in a cauliflower shape. Meteorologists classify clouds according to their basic shapes and the height of their bases above the ground. Whether or not a cloud generates precipitation, and if so, what type, is also a consideration. Cloud classification is not an exact science because cloud shapes are not always distinct. Through time, a single cloud may change shape, blend with other clouds, or evolve into a completely different type of cloud as conditions change. In addition, several types of clouds, with different forms and with bases at different levels, can sometimes be seen in the sky at the same time. Although cloud forms are ever-changing, they are not arbitrary, but instead reflect processes operating in the atmosphere. This is why a knowledge of cloud types often provides clues about future weather conditions. The simplest distinction is between stratus, cumulus, and cirrus clouds. Stratiform clouds display layers and generally develop under what meteorologists refer to as stable conditions. These conditions reduce the tendency of the air to rise. An inversion layer, or warm air lying above cool air, results in an extremely stable condition because temperatures increase rather than decrease with altitude. This inhibits rising air movement and can lead to the development of smog over cities as pollutants are trapped under the inversion layer. Unstable atmospheric conditions are those in which vertical air movement, once started, is likely to continue. This leads to the development of puffy, cauliflower-like shapes of cumulus clouds. High-altitude cirrus clouds are made up of ice crystals and are fibrous in appearance. The criteria of height added to shape allows meteorologists to classify clouds into 10 types or genera. Even in a day of satellite images and instant communication, being able to recognize these cloud types and the weather patterns commonly associated with them is a useful skill. Low clouds have bases that lie within 2,000 meters or 6,500 feet of the Earth's surface. These clouds are generally made up of water droplets rather than ice crystals, and their formation is usually influenced by conditions at the Earth's surface, such as combinations of temperature and topography. There are 3 basic types of low clouds: stratus, stratocumulus, and nimbostratus. Stratus clouds are low to the ground, covering the sky from horizon to horizon with a dull grayness. Some stratus clouds are so low that their bases actually touch the ground, in which case they are referred to as fog. Most common in the early morning, fog and low stratus layers may lift as the day warms. As the stratus layer lifts, it may break up into stratocumulus clouds. These clouds are also low, but their rounded, puffy forms give them much more visual character. From below, stratocumulus clouds often appear as whitish masses with dark gray areas in their thicker portions. Their lumpy bases are often higher than the condensation level. Although stratocumulus clouds sometimes appear as ominously dark masses, they do not yield large amounts of precipitation. Wind and increasing temperature are important agents in breaking up a stratocumulus layer. Through the day, occasional blue holes and spots of sun may be seen. If the winds continue, a cloudy sky may clear with only a few scattered clouds visible at sunset. Nimbus, a term meaning rain, forms the prefix for nimbostratus clouds, low clouds that yield significant amounts of precipitation. These clouds are usually somewhat darker than stratus clouds, but equally featureless. Rain or snow falling from such clouds is generally light to moderate, but may continue for hours on end. Middle altitude clouds have bases between about 2,000 and 6,000 meters, or 6,500 and 20,000 feet. Temperatures toward the higher end of this elevation range are generally below freezing, so these clouds are often composed of mixed ice crystals and supercooled water droplets. The two basic types are altostratus clouds and altocumulus clouds. Altostratus clouds stretch across the sky as gray to bluish-white layers that may have either a striated or dully uniform appearance. They often form when warm air rides over cool air ahead of a warm front and can frequently be seen moving over a sky dotted with cumulus clouds. Altostratus layers are rarely thick enough to completely obscure the sun, so it shines dimly as if through a pane of frosted glass. This pale sun may be surrounded by a corona, indicating that the cloud is formed of smaller than usual water droplets or ice crystals that bend or diffract the sunlight. At night, such a corona may also surround the moon. Altostratus clouds rarely produce much precipitation, but these clouds may lower and thicken into nimbostratus layers. Altocumulus clouds are middle-level clouds with a billowy, cumuliform structure. They often appear as gray and white cloudlets regularly arranged in waves of more or less parallel rows. These cloudlets appear to move as a unit at speeds dependent upon the wind. The cloudlet shapes are distinctly rounded and shaded in contrast with higher cirrocumulus clouds. Altocumulus clouds are especially striking at sunrise or sunset, when their shapes are embellished by the reflection of red, orange, and brilliant yellow light. A variety of this cloud type, called altocumulus castellanus, cloud castles, are formed spontaneously as heat is released when condensation occurs. This is a sign that medium-level air is moist and unstable, and rainy weather may soon follow. Another manifestation of this cloud type is the altocumulus lenticularis, or wave cloud. These are formed by wind flow over hills or mountains, as here over the summit of Washington's Mount Rainier. Once formed, lenticular clouds remain stationary in the sky as long as the wind speed remains constant. High-altitude clouds, with bases above 6,000 meters, or 20,000 feet, have distinctive forms because they are composed mostly or entirely of ice particles. Because high-altitude clouds are nearly transparent, the sun and moon shine through, but are often circled by a well-defined halo that forms a much larger ring than the corona associated with middle-altitude clouds. The composition of ice particles gives these clouds a wispy or fibrous appearance. These clouds are all referred to as cirrus clouds, from the Latin word meaning a curl of hair. The three basic high cloud types are cirrus, cirrostratus, and cirrocumulus. Cirrus clouds are composed of delicate white filaments that are nearly transparent. Strong, high-altitude winds blow streaks of ice crystals away from the heads of the clouds and toward slower-moving air masses. These falling streaks of ice particles are sometimes called mare's tails. When moving ahead of a storm system, the mare's tails point toward the warm air mass. Cirrus clouds, followed by a layer of cirrostratus, are often the advance agents of frontal systems and bad weather. Cirrostratus clouds form a high, thin veil that gives the sky a milky blue-white appearance. Cirrostratus clouds may have a fibrous appearance and often indicate the approach of a storm system. Cirrocumulus are high-altitude clouds that appear as a white sheet, made up of smaller individual cloudlets in a grainy or ripple form. Cirrocumulus cloud puffs appear smaller in size than the sun or moon, show very little gray shading, and are generally arranged in rows. This pattern of high cloud is sometimes called a mackerel sky because it resembles the markings on the back of this type of fish. Least common of the 10 cloud genera, these clouds may be seen in combination with cirrus or cirrostratus clouds. Although not a natural formation, persistent jet contrails indicate that air aloft is near saturation, and under such conditions may add to the overall cloudiness at high altitudes. A fourth category of clouds extend from low bases to great heights. These clouds of vertical development take cumulus and cumulonimbus forms. Cumulus clouds are the familiar puffy white clouds seen against a vivid blue sky. They are formed by convection in rising bubbles of hot air that develop as the Earth heats during the day. If the surface air is sufficiently moist and conditions less stable, small puffs of cumulus cloud typically appear by mid-morning. As the Earth continues to heat, these clouds begin to merge with each other and grow vertically. Cumulus clouds usually grow to their greatest height soon after the surface air temperature reaches the high point in early afternoon. During the later afternoon and early evening, fair weather cumulus clouds flatten and thin as the cooling Earth's surface reduces the supply of rising warm, moist air. When many cumulus clouds develop early in the day, showers may occur later as the clouds reach greater heights. A shower may be followed by a rainbow produced as sunlight shines on raindrops. If atmospheric conditions are highly unstable, cumulus clouds continue to grow vertically until they become the towering thunderheads called cumulonimbus clouds. These dense, dramatic clouds have great vertical extent and may grow to the bottom of the stratosphere. The fully developed cumulonimbus cloud's upper portion is flattened and forms a vast plume or anvil of ice crystals spread by high-altitude winds. Cumulonimbus clouds along an advancing frontal system often develop squall lines that extend for hundreds of miles. These squall lines may bring high winds, heavy rain, lightning, and hail. These storms may even generate the most violent and destructive of weather events, tornadoes. Because cumulonimbus clouds lift huge amounts of water vapor into the middle and upper atmosphere, residual patches of cloud may persist in the sky for hours after the thunderstorms dissipate. As the clouds trace intricate patterns across the Earth, or evolve from one type into another, they herald changes in the weather. When we read the clouds, we gain a better understanding of patterns in the weather.